Hello. Today we wrote a contest, stage 19 Estonia, the second Universal Cup. And during the round, I was able to come up with a solution of problem F. Problem F. When Anton saw this task, he reacted with sad smile, with a frown. Well, so in this problem, we need to write heavy light decomposition and a segment tree on matrices. So there are actually two parts of the solution which we need to implement. Sorry, I need to close this. Yeah. Okay. So what the problem is about? We have a tree. In each leaf there is a vector of R3. And in each vertex there is also a vector, which is equal the vector written in its left child cross product the vector in the right child. And we need to calculate the vector written in the root of the tree. But not only that, we also need to update the leaves. So there can be a query which is said we have a vector vk in the leaf, we need to replace it with some vector vk prime, and then we need to somehow update the vector written in the root. And we need to perform all these queries. So we will have 100,000 updates, and the tree is of size 2 times 200,000. Well, how do we solve this problem? To solve this problem, we store. So let's represent our tree as a union of several paths, disjoint union of several paths. Then, what do we want to do? So actually, when we update some vertex, some leaf, only vertices that are updated are on the path from this vertex to the root. Yeah. So only these vertices have something updated. And if we were guaranteed that the height of this tree is at most logarithm, for example, then the problem would be easy. Yeah, because we simply update all these vertices. However, it's not the case. Usually the height of this tree is much bigger than logarithm. So we need to use heavy light decomposition. And we know that although the height, the depth of the vertex might not be logarithmic, definitely the number of paths, I think they're called heavy, the number of heavy paths on the path from the vertex to the root is at most logarithm. So this is known in heavy light decomposition. It's known how to do it. Let's think what we can do about it. So actually, there are two things. First of all, when this is updated, the first path, it is always... So what do we need to store in the path? In the path we need to store the function of the following kind. What do we get in the root of the tree if in the lower vertex of the tree we have some vector? So we need to store a function from vectors to vectors which corresponds to what happens from the lower point of the path, to the upper point of the path. We cannot store any arbitrary function, but this function is actually linear, so it is just a linear mapping linear function, which can be stored as a matrix 3 by 3. So we store a matrix. However, it's not enough, because we don't always come from the lower point to the upper point. Unfortunately, sometimes, for example, in this case, after we have jumped here, we need to traverse from this vertex to this vertex. This is harder. This is harder because now we also need to jump from a vertex to... Okay, what I mean is we need to jump from this vertex to this vertex. Yeah? And we need to do it from the middle of the path. We need to do it from the middle of the path. However, it's still easy because it is segment 3. We can do it with segment 3. So we don't store only one matrix. We store a segment 3 on these matrices. And when we are in the middle of the path, we ask for the prefix product of these matrices, and we come here. That's it, actually. So there are two parts. We need to create a heavy light decomposition, and we need to make a segment tree on matrices. Let's do the both. So, okay, we will start actually with input. So for input we only need IOStream, maybe we need vector to store it. VI, actually it is a tree, so we need to store we get the left and the right child. What is X? What? It's just a symbol. What was the reason to do it? Interesting. Okay, so we always can store a vertex as a bool and 3 ints. Yeah? So each vertex is a bool and 3 ints. Let me think. So how do we store a vertex? How do we store a vertex? Okay, for now let's store a bool and 3 ints. So let's call it a vertex row. So it's bool leaf and int xyz. Okay. Actually, we can write a function of reading. So friend friend iStream greater iStream in vertex row v. So we need to read a char, and if it is an x, then it is an inner vertex. So we say that v dot leaf is false. Then we read x and y. We say that v z, for example, is 0, and also we would like to decrement v.x and v.y. Otherwise, we simply read all numbers. So we say v.leave. Actually, let's say v.leave is that it is v. And here we need to just read all elements. Okay. We are happy. So we have read the vertex. Also, we need to read the query, and query looks like number of vertex and the new vector. Actually, let's let me think. Actually, let's also make a vector. I mean, let's store. Yeah, let's store a vector. So I would like to have vector 3D. So vector 3D is simply, for example, array in 3. And to do that, we need to include array. Yes. What's wrong still? You need... Yeah. And I guess we can implement operator brackets. Yes, and we can do the same thing with const. And now we can store in this query v3g. And we can as well read it, I think. And here we read if this was an error. Here we read the vi. Also, we can read the query in kind of same manner. To do that, we need to read the number of vertex. They both vector and vertex. So let's call it W, for example. Okay, we have read the query, and I guess that's it. Now let's write the function solve test. To solve test, we need to firstly read N and Q. Well, we can also store, we can create a test. In the test, what do we need to store? We need to store, we need to store the tree and the queries. So we need vector vertex row, vertices, and a vector query queries. Yeah, so to read it, we need to read N and Q. Then we need to read and also query. What's wrong? Ah, test should be T. Okay, we read all the queries. Okay, and we return in. Yes. Now let's solve test. So to do that we need test T. And then we need to print the answer. So the answer is simply a vector of 3Ds. Okay, let's also write the function which outputs the vector. And this is simple, we just need to firstly print a space. Then we need to print vi. Excellent. So we need to... Let's actually make a struct test ans, which is a vector of v3d So for v3d a vector from v testans.v, we need to print v, and then we return output. I'm doing it because I feel like I will need to make stress, and in order to do that I make everything comfortable from the beginning. Well, now we need to write function main. Also solve tests. Sorry. Yeah, solve tests. And finally, main. So actually reading the input already took a lot of time, which is a bit pitiful. Okay, we have done with reading the input. It is already 100 lines. Now we need to find answer only. Okay, so we need a heavy light decomposition, and it is just what? So what do we need to store in heavy light decomposition? Heavy light decomposition will be a set of paths. Yeah, a set of paths. So for each of the paths, we store. Let me think. What do we need? So first of all, for each vertex, we need to store the number of paths in which it lies and its index in this path. Okay? For each path, we need to store the segment tree, and also we need to store its parent. Yeah, we need to store its parent. And also the root should not be in any path. The root should not be in any path. And for each path, we store the segment tree, which says what does it take to go here in this vertex. Okay. So now we need the segment tree. And to do that, let's start with the matrix. Struct matrix 3, 3. So matrix 3, 3 consists of three vectors. Now we need to write some function. We need only multiplication actually. We need several things. Let me think. Yeah, actually we need first of all we need a constructor. So m33 of v3d and bool left. Okay, so what do I mean by that? When we have a vector A and vector B, we want to represent A as a matrix 3 by 3, which needs to be multiplied by B to get a new vector. And bool left means that A is left of these two multiplicants, because also we can represent B times A, B cross A as this thing, but in this case it will be minus the same vector. So let's think how it looks like. So here we need AYBZ minus AZBY. So we need 0 minus AZBY. I see. So first of all, let's just make this. When we always work from the left. So we say that M01 is minus M3, M2. M02 is M minus M2, actually M1. Not M, but V. Okay. Oh, 1, 0 is V2. 1, 2 is minus V0. 2, 0 is minus V1. And 2, 1 is V0. And here we need to say that M33 of V, but if not left, then everything should be negated. So this equals minus this. Let's also write the negation. To do that, let's make a new matrix which equals the old one and negate all its okay, and to do that we also need to make the negation for V3D, but it's easier. A. So, but instead of x equals minus x, we need to say that x equals difference of x of 0 and x. What is difference? So actually we work modulo this modulus, so we need to write what? This was not correct. Okay, yeah, we need to do like this, but here we need ans. Ans dot A. Okay, let's write the difference. And also we will need product, of course. Also, we would like product LL. And we will need some LL. And we will need product. So here we return this. And also we will need prod LL, where we just return A times B, I think. So we have functions for integer summation modulo m and long summation and multiplication modulo m squared. Okay, now we're ready to write the multiplication of matrices. Okay, so how do we multiply the matrices? So M33 ounce. M33 ounce. So here, let's do the following. So we go through the columns of the first matrix and the rows of the second matrix. So we say that A equals sum LL of A and we need to put here M33 other. So here we need V ij, VIK, and other dot M IK and other dot M AJ. And then in the end we say that ans dot M. Okay, let's actually write the operator square brackets. It's done like this. Yes? Is it done like this? No, it's not. Okay. Okay. Let me think. Okay, excellent. Excellent. We have written the multiplication of matrices. Also, let's make the matrix of ID. Static M33 ID. Okay, we have written also the matrix ID. Now I guess we are ready to write a segment tree. So segment tree stores M33 V, I think. So let's extract it. Segment tree Actually, it's not trivial. So let's exactly. Okay, we will definitely need segment tree. So it's not a good thing that I'm hesitating here, but still. So if we have n matrices, we will need two n here. Okay, well, we need int this. Here we need m.size. Let's write a function build tree. To do that, we need to go through from n minus 1 to 1, and we need to. Okay, let's also write a function update. And here we say that vk is v2 times k times v2 times k plus 1. And here we need to simply update vertex of I. So here we need to transfer m to a v, and it is done via copy. Copy m.begin, m.end, v.begin plus n, and then build tree. Now we need two functions, which is prefix product and update. Let's make both of them. First of all, we need an update. Okay, first of all, we need an update. Let me think. Okay, update is easy. Update is easy. So what do we need? We need an index and new matrix. So what do we need to do? We need to say that v index plus equals n, v index is equal to matrix, and while index is at least 1, yeah, while index, we need to say that while index is divided by 2, we need to say that update vertex index. That's it. Now let's think, what do we need about mass operations? So when we have a path and we have another path, so we know what vector is written here. We need to calculate what vector will be written here then. Yeah, so let's assume that we know. So we need to know. Oh, it's a problem. Actually, I think it is a problem. So no, we cannot calculate it. We can only calculate what is written here. Yeah, we can calculate what is written here. So we can calculate what is written here, but it's impossible to update it so we can know what is written here. Okay, so first of all, we can jump to the top vertex of the path. It is easy because it is simply a prefix question. Also, we will need to calculate what is written here after that. Yes? To do that, it is simply the combination of this and this. So here we know the vector, so we would like to know the matrix of this, the vector in this vertex. But in order to calculate it, we will need the matrix in this vertex. And we need a suffix query. So we need both prefix query and suffix query. And also we need to know what is written here. I think it will be stored in our HLD. So for each path, we know what is stored in its lower point and what is stored in its lower point and what is stored. Actually, lower point is always a leaf. Yeah, I think so. So we know what is stored in the leaf, so we can calculate this thing, and then we can calculate this thing. So we need a suffix query and a prefix query. So let's just make a subsegment query. So M33 product from L to R, inclusive L, exclusive R. So we store M33 left equals M33 ID and right equals M33 ID. And then we return left times right, L plus equals N, R plus equals N, while L is less than R, we do the following. So if L is odd, then left is left times VL, but we need to increment it. If R is odd, then we decrement R, and then we divide both by 2. Okay, I think that's it. So now we have a segment tree. Now we need to write a heavy light decomposition. It's already 44 minutes. Okay, again, so what do we need to store for every path? Let me think. Okay, I know what we need. First of all, we need for every okay, let's make a struct path, I think. So what do we need for a path? For a path, we need, first of all, segment tree. Yeah. Secondly, we need a number of vertex, which is its the number of its lower and upper vertex. Well, I think we can just store all the vertices. Let's just store all vertices of the path. I think it's reasonable. Finally, I would like to also for each vertex, I want to know in which, okay, let's store two vectors in which path and at what position in this path for each vertex. Do we need anything else? For each path we store the set of vertices, it's segment 3. Also, I need to store a parent. For each vertex we need a parent. Anything else? And for each vertex, if it is a leaf, we need to store its vector. So in find ans, we can need to construct a HLD given ans dot what? The given test dot queries. Yes. Not test.queries, but test.vertices. And after that, we need to iterate our queries. Okay, we can do it quite naively. We can say ans.v.resize test.queries.size, and for int I equals 0 I less than test.queries.size, we can say that first of all in HLD we need to update leaf v with, okay, we can just make a query here. I think query is fine. And after that, we need to say that answer.vi equals hld dot calculate in root and return answer. So we need two functions, three functions. We need a constructor, we need update leaf, and we need to calculate in root. So calculate in root is the easiest one. Let's write it. v3d calculate in root. So what do we need? We know that root is the vertex number 0. So first of all, we need to find the path in which this vertex lies. After that, we need to find its leaf. Okay. Actually, we can calculate in any vertex. We can calculate in any vertex. So first of all, we need to calculate in which path index. We go to the leaf of this path. Then we know that its vector is v3d of vectors. So let's say vectors leaf. Now we need to substitute it. Now we need to substitute it in a matrix, in the matrix which corresponds to path from the leaf to the vertex number index. This is easy. We need to take path dot segment tree and find the product of what? So let's think. For example, okay, we have path from like 0, 1, 2, and 3, and we need to calculate in this vertex something. We need to calculate something in this vertex. Actually, if the path is of size 3, then actually there will be only two matrices. The matrix corresponding to this, and to this. So if we want to come from 3 to 2, we only need one matrix. So segment, if the path consists of 4 vertices, then there are only 3 matrices. So I need to say that we need a product from at what position of index to at what position of leaf. Okay, we have found this product. Then we need to multiply by it our vectors leaf. And that's basically it. So this was pretty easy. However, we didn't write the multiplication of a matrix by vector, so we need to do it. So let's calculate int answer. We can store ll answer, return answer %m, but here for I from 0 to 3, we say that answer is sum ll of answer and prod ll of what? Of v. No, it's not that simple. Actually, okay. We need to do like this. So we need v3d ans. And here we say that ans I is I times r. Okay, so what we need to do is write the scalar product of two v3ds. And here we need to do llans equals 0. And from I equals 0 to 3, Fans is some level of fans and product. I think vi and other I, which is v a again, and return answer percent n, and not v3d but int. Okay. So now, what's wrong now? Product is what? Product is m33? Yes, and it is what's wrong with you? No suitable... Oh, okay. So we need to remove it from here, put it here. Yes, now it's correct. Still nothing. What's product? Product is... now it's fine. Yes, so we have written one of three functions. Now we need to update leaf and HLD constructor. I think let's write the constructor. Okay, so we still don't know. We still don't know how many paths there will be, but we already know that in which path is vertices dot size -1, at what position is also vertices dot size and -1. What else? Parent is of size n, paths we don't know, and vectors we know. Okay, so parent vertices dot size -1 and vectors. Excellent. So we've done it. Now let's think how we... So let's do the easier ones. So vectors is quite easy. So let's go through all vertices. So if vertices I dot leaf, then we know that vectors I is simply vertices I dot xyz. Actually, I think we need a pair of braces. Okay, if it is not a leaf, then we know parents of two vertices. So we know that parent of vectors vertices I dot x is I, and for y the same. Good. Okay, we have filled parent and vectors correctly. We still don't know the paths because we still haven't constructed the heavy decomposition. So to do that, Will we need a DFS? I don't know how it's best written. So we make, first of all, we need for all vertices to know their size of subtree. Then for each vertex, like we simply know it's subtree, yeah? Okay, I'll be right back. Let's continue. So I think we will need the following. First, we'll need to calculate the size of all sizes of all subtrees. So we only need. We will use a vector of the row vertices. So how do we do it? We do it with DFS actually. What do we do in the DFS? Function is undefined because we need to include functional. So if size of subtree should be what? Should be number of vertices. So let's just say that initially it's all ones. So if vertices v is not a leaf, then we need to run DFS for both children. And add their sizes to our size. I think we can just do like this. Okay. Okay, it's excellent. It is excellent. It is excellent. Okay. So we have calculated the sizes of subtrees. Now we need to create paths. And also we will need this nice vector. Okay, in order to do that, let's first of all calculate the size of subtrees. Then we will need another one DFS, which creates the paths. Actually, create path sets. Okay. Let me think. Let me think. Okay, yeah, that's fine. We will create path sets. So what does this function DFS do? So Ah, we need to run this DFS. And here we also need to run this DFS. Okay, let's look at our vertex. So if it is a leaf, let me think. Okay, so let's look at our vertex. If it is in some path, yeah, so if in which path v is not -1, is -1, then we need to create a new path. So we say we need to make a empty segment tree here. But it is fine to do. So paths dot in which path v equals paths dot size, at what position is 0, and we need to add a new path. And we need to put this vertex into this path. Okay, now if it is not a leaf, then we need to look at the bigger of its children. So if subtree size of vertices v dot x, okay, let's just write that L equals vertices dot x and R is vertices v dot y. So if subtree size of L is at least subtree size of R, then we will need to go to the left child. So we say that paths, let's do like this. Paths in which path dot vertices dot pushback L, and in which path V is in which path L, in which path L is in which path V, and at what position L is at what position V plus 1. Else the same thing with R. R, great. And then we need to run DFS of L and DFS of R. So we have created path sets, and now we need to create simply paths. What do I mean by that? Okay, now we have a small problem. That what do we have now? We definitely have in which path. We do have at what position. We have parent, we have vectors, and in paths we have vertices, but we don't have the segment trees. So the only thing that is left is to construct segment trees. So let's create path sets, and then we need to create segment trees, and it can be done for each path independently. Let's call it like fill path. And I can make it a lambda. So let's fill the path. So to fill the path, for each vertex except the lower one, except the leaf, we need to create the matrix. Yes, so let's do it. Let's do it. Okay. Unfortunately, so I think we need to calculate this thing vectors for all children. What do we need to do? I mean, we need to calculate it. Yeah, we need to calculate it actually for all vertices, I think. We need to calculate it for all vertices. We need to know it for every upper vertex, not only lower vertex. This is a problem. So we can do it in a separate function. So void fill vectors. And this is one more DFS. So if vertices v is leaf, then we simply say that vectors v is vertex is this vector. But else vectors v is the product of its left and right children. So we say that it is vectors vertices v dot x times vectors vertices v dot y. Actually, it is incorrect. It's not correct. I don't need to multiply them like that. It is not true. I need to make a cross product. I need to make a cross product. How do I make a cross product? What? Ah, here it is. So I'm not ready here to make a cross product. Where is it? Yeah. So friend greater percent of v3d v3d a, v3d b. This is kind of easy to calculate it. We need to take m33 of a and multiply it by b. So simple. Great. Okay, now we are able to make this percent function. What's wrong with you? I think I don't need to make it friend because for some reason it can't find it. So let's just call it with v3d operator percent. Can I do it? I can do it if I declare it. Yeah, I need to declare it. So here I need to write like this. And now, does it work now? Yeah, now it works. And again, I need to run the effects of 0 to fill the vectors. Excellent. Now, when all vectors are known, I am able to calculate let's, instead of calculating root, I will write it getting root. Yeah, and to get in root, I need to return get in vertex 0. And get in vertex is also const v3d. And I need to just return. Oh, I think no. I think okay, it's fine actually. So get in vertex is simply return vectors index. Yes. And actually, when calculating root, I would like to say that here we say that we update it in a vertex index. Okay. Yes. Yes. Okay, so let's create paths. So we need to fill a path. To do that, we need to first of all make a vector of matrices. We will fill this vector. It actually will be of size path dot vertices dot size -1, and then we will say that path dot segment tree equals segment tree of matrices. Now let's fill it. So what is matrices I? Matrices I is the matrix which is needed to calculate the value in point I. And for that we need to take its children and calculate for them. So let's look first of all at our vertex. Our vertex is path dot vertices I. So int other child, let's call for example equals vertices vertex dot x, but if other child for some reason equals vertex equals path dot vertices I plus 1, then we need to take the other child. Okay, now we have the other child. Okay, let's also store if our other child is left or right. Bool left other child equals, is it true that vertices vertex x is not equal to path dot vertices I plus 1? Then we say that other child is, if it is left, then take x, else take y. Great. And then we say that matrices I is M33 of vectors of other child and left other child. Actually, it should be another child, so let's rename. Okay, the problem with that is that vectors is not obligated to store everything about everything, but another child is a top vertex of a path. So we will need to fill it updated always, at all costs. So we need to fill vectors here. So let's fill vectors of vertices and fill and construct and how it's called? Create paths of vertices. Now it's more or less fine. Yeah, it's more or less fine, and we only need on one function, update leaf. So what does it do? We need to take vertex v, update its value with w, and update all upper vertices, all like paths, all upper vertices, elements, and that something like that. Okay, let's go. Let's go. Okay, int current vertex equals q.v. Then we say that vectors of current vertex is q.w. Okay, if only that would be enough, we would be happy, but no. Unfortunately, no. Now, what do we have? So our current path is not... So we want to jump to our... We need to update our upper vertex. And current vertex actually will be always the upper vertex, or no? Yes, I think our current vertex should be always the upper vertex. So we also would like to store current path. Okay, current path is not needed. We only need current vertex. Okay, so we can say that current vertex is in which path current vertex. Then we need to take this path vertices dot front. I would like to have... Okay, it doesn't matter. It's fine. So I need to update this current vertex. So I need to calculate in vertex current vertex. Yes. Now, while current vertex, so while it is not a root, let's do something. So we are currently in the upper vertex of some path. Let's jump in the next path. Let's jump in the next path. So int parent equals parents. Oh, wait, what is that? Do we have parents? No, we only have parent. Okay. Well, it's not needed. Okay, so let's see. Let's see. So let's take parent of current vertex. So we have a parent. Let's store if we are left or right child. So bool left child equals, is it true that... So we need, for each vertex, for each parent, we need to know if we are left child or a right child. We can actually store it here. So let's say that we have a vector bool left child. Yeah. So here, when we do this, we say that left child of this thing is true. And here we need to say that what? So where is left child actually? Left child is right after parent. Left child is right after parent. Okay. Yeah, we need to update vertex, update leaf. Okay, we know that if we are left child or not, so let's take it. No, left child of current vertex simply. Okay, now we know if we are left child or right child, or right child. Then let's construct our matrix, which is M33 of this thing. So this is the bool, and also we need the vectors of current vertex. Okay, this is a matrix, which is a new value somewhere. The question is where? The answer is, so we need to take paths of our parent. So we need to say in which path our parent lies. Actually, not in which path, but at what position. And this matrix with this number should be updated with this matrix. So we need to take paths in which path. Okay, let's actually make temporary variable. Our parent equals parent of current vertex. So we need to take paths of our parent. Take its segment tree and update it. What is update vertex? Okay, update. At what position this parent is with this matrix. It is great. After that, we need to say that current vertex is actually the leading vertex of this path. And we need again to recalculate this vertex. That's actually it. We have written it. It is ready. Let's try to compile now. It compiled. Maybe it will also work, although I somehow am not sure. I don't think it worked, because there might be something wrong. Okay, update vertex failed because v is of size 4, but we asked for update vertex of 3. Why did we do it? Because we asked for update in which path? At what position our parent? Our parent is 2, and it is at position 1. I see. Because what is n? N is 2, so index was 3. Now index should be 1 actually, but it is still 3. What? Yes. Easy bug. It worked, but still negative numbers don't feel right, I think. Okay, let's look at our HLD. I think firstly we need to look in the constructor. Yeah, because we filled all vectors. Vectors of size 5. So leaves, I don't know what leaves are. Zero, 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 zero. Did we fill vectors or not? Why nothing is filled? Nothing is filled. Let's look into it. Ah, we didn't run DFS. It's funny. So we need to run DFS of vertices X and vertices Y. Okay, did we make it now? 1, 1, 1, 2, 0, 2, 1. Some huge numbers which shouldn't be here, I believe. And 1, 0, 1. Okay, why are there so big numbers? Maybe I think matrix multiplication is wrong. So what are children? 1 and 2? Okay, are 1 and 2 correct? 1 is this and 2 is failed. 2 is not correct. Let's look into 2. Okay, 2 has children 3 and 4. 3 and 4 are fine. So I believe this is the problem. No, it's not a problem. Okay, so V is this matrix. Then we fill it somehow. And now it... What is that? Ah, yeah. I needed to make differences. Okay, let's check again. It's still nothing good. Let's try again. Yes, first of all, we need to make this matrix. And is it correct? What is that? Why is this? What? Ah. Ah, because it should be... We need to initialize it. Unfortunately, we need to initialize it or it is not good. But we also... I think we simply need to initialize v3d. So v3d should have a constructor. If we did it, does it work? Or not? No? Can I initialize A with a constant value? No. No instance matches. Okay. Okay, I hate it a bit, but let's make a constructor. And we can make a default constructor by replacing it with zeros. No. Ah. Let's check it again. Yes, it is more or less fine. Yeah, it is more or less fine. Let's look into the answer, and it is correct actually. Yeah. So if I submit it right now, I won't get a VR1. It's VA2 at least. Okay, let's submit. Actually, let's start with a custom test. Let's start with custom test. Judging test 2, and it's infinite cycle. No, it's accepted. Well, it's the first try, but still it was a long journey of 360 lines and almost 2 hours. Well, I managed to do it, though it's not for me writing it during the contest, but still, thank you for watching.